My name is Ben Pruthi, and I'm going to be presenting on combining the fragmentation approach and neural network potential energy surfaces of fragments for accurate calculation of protein energy. Accurate force fields are critical to many protein-related simulations, including protein folding, protein ligand docking, and protease catalysis. Essentially, an energy surface for a molecule with n atoms is a 3n dimensional surface in R 3n plus 1, where the input vector represents the positions of the various atoms in a given molecule, and the output, a scalar, represents the total energy of the surface. Given the physical relationship between the force and potential energy, the negative gradient of this total potential energy will give the x, y, and z components of the force on each atom. In this example, which is reduced to a two-dimensional surface for simplicity, a protein would have a stable equilibrium state at the origin since the energy surface is a relative minimum at this point. Using standard full system quantum mechanical methods of calculating total protein energy is too expensive to be practical. Thus, for large protein systems, fragment-based methods are being explored, which reduce the cost of quantum mechanical simulations. Essentially, this involves considering a large system to be composed of two or more independent systems. The accuracy of this approximation decreases if the subsystems have significant interactions. This process can cause a k to the p minus 1 speedup, where k is the number of fragments. Since quantum mechanical algorithms tend to be O of n to the 6th or 7th, this process can give significant improvements to efficiency. Furthermore, since subsystems can be processed in parallel, the real-world simulation time is even further reduced. Various types of fragment-based quantum mechanical methods have been developed recently. These can largely be divided into two categories. First, we have those based on the inclusion-exclusion principle, or IEP. This includes molecular fractionation with conjugate caps, or MFCC. With these methods, systems overlap, and the total energy is the sum of the fragments minus the energy of the overlapping areas, as you can see here. Next, there's many-body expansion theory. These methods involve non-overlapping fragments, which is good for molecular clusters and crystals or proteins that do not have covalent bonds between fragments. Combinations of the two methods have also been employed recently. For example, some methods use the simpler MBE for non-covalent fragments and IEP for bonded fragments. Calculating the energy of each fragment can still be computationally expensive. Machine learning has reduced this cost, allowing for efficient, reliable predictions of physicochemical properties of molecules, constructions of force fields, and constructing potential surfaces. This study used neural network generalized molecular fractionation with conjugate caps, or NN-GMFCC. The protein is divided into 20 residue fragments and one conjugate cap fragment. Machine learning methods, specifically neural networks, are used to calculate the total energy of protein fragments. The study demonstrates that NN-GMFCC yields results that accurately match those from previous fragment-based quantum mechanical approaches in orders of magnitude less computation time. As described before, the protein is divided into 21 fragments. A conjugate cap, shown here, is used to saturate dangling bonds so that all fragments are terminated with an acetyl group and an N-methylamide group. Here, the energy of each fragment is summed up, the energy of the caps that were added is subtracted out, and the interaction energy of side chains from separate fragments is added. These are calculated using molecular mechanics as opposed to quantum mechanics for efficiency. Most of this contribution comes from electrostatic and van der Waals forces. Similar processes to the standard method were used with this neural network method. In this case, though, the neural network replaced the quantum mechanical algorithms for calculating the energy of each fragment. 21 neural network models are trained, and each corresponded to a different fragment. There were 20 residue fragments and then your one conjugate cap. Data from molecular dynamic simulations are used to train the models, and molecular mechanics is still used for interfragment interactions because there are no neural network models for interfragment interactions since it uses an O of n squared algorithm. So with 20 fragments, you would have 400 residue fragment pairs. In this study, NN-GMFCC and GMFCC-MM methods were applied to 14 protein structures from the protein databank after bad contacts were removed using the AMBER-16 program, which my mentor, Carlos Simmerling, helped to develop. Protein energy were calculated at a consistent level, and quantum mechanical calculations were completed with the Gaussian 9 program. CPU time of both methods were computed using the same processor, and from 3 selected proteins, snapshots were extracted to examine whether the 2 simulations yielded comparable results. As you can see here, E sub nn is the sum of the contributions from each atom, which depend on the atomic local chemical environment. Neural network parameters came from experimentation or training data. In this work, a local environment matrix with the end-to-end model was used as descriptor G. This gives the radial and angular information about the effects on atom I from some atom J. The training of the neural networks is carried out using DPM-DKIP to ensure proper parameterization and weighting. Next, replica exchange molecular dynamics or REMD simulations were run using AMBER 16. For each fragment, 20,000 conformations were taken from REMD and their corresponding energies were captured. One common protonation state is taken for each residue, though with multiple residues, a wide variety of variants were sampled, as you can see on these plots below. This allowed for the network to be accurate for a wide variety of states. For each sampled fragment, energy ranges were calculated, giving a baseline estimate of protein energy, but an energy cutoff was not set for training data since a fragment presented to the neural network may have a potential energy outside of the range of the training data. Next, root mean squared error was calculated for the total energies and atomic forces of the 21 fragments with respect to calculations made using a discrete Fourier transform indicated by the DFT here, using these formulas. M here is the number of conformations and N is the number of atoms. The RMSEs of fragment energies in both training and testing sets never exceeded 1 kilocalorie per mole. CTRP had the largest RMSE in the training data sets, which is 0.98 kilocalories per mole. The RMFCs of atomic forces in both training and data and testing sets is no more than 1.3 kilocalories per mole. Once again, CTRP had the largest error of 1.28 kilocalories per mole angstrom. It's possible that the CTRP had such a large error because it had the most atoms of the 21 fragments. Accuracy of the NN potential energy surfaces for all fragments ensures that the total protein energy will be accurate. 14 different proteins were downloaded from PDB with between 243 and 13,728 atoms each to test the accuracy of the NN-GMFCC approach. Deviations of the two approaches are shown in this table here. All error came from the fragment's internal energy since molecular mechanics was used to calculate the interactions between separate fragments in both methods. The energy and atomic forces for each capped residue found with the neural network were calculated and found to be in excellent agreement with corresponding GMFCC MM results. Mean unsigned errors of the energy deviations and atomic force RMSEs is given by NN-GMFCC, which is 201 kilocalories per mole and 0.68 kilocalories per mole angstrom with respect to GMFCC MM calculations. The deviation of NN-GMFCC is only negative 0.87 kilocalories per mole for the largest protein, which had 13,728 atoms. Deviations of energy and atomic forces did not increase with the size of the protein system. For all protein systems tested, RMSEs of atomic forces never exceeded 0.9 kilocalories per mole angstrom. Here you can see a comparison of the atomic forces between the two methods. The NN-GMFCC allowed for calculating protein energy in seconds with accuracy comparable to a quantum mechanical approach. Figure 6 shows the computational timescale and energy errors of the 14 tested protein systems, shown here. As you can see, both GMFCC-MM and NN-GMFCC scale linearly, though the NN-GMFCC are about 4 orders of magnitude faster. In conclusion, a new NN-GMFCC method based on the GMFCC-MM approach combined with the neural network high-dimensional potential energy surface was developed. This method can obtain high accurate total energies and atomic forces within seconds. Fragment neural networks were built with a DPM-DKIP program and MM force fields were used to model two-body interactions between residue pairs. For the protein systems tested, which had up to 13,728 atoms each, the energy deviations and atomic force RMEs were 201 kilocalories per mole and 0.68 kilocalories per mole angstrom, respectively. Relative energies of various proteins were also calculated using the new method, and all of the MUEs, mean unsigned errors, are less than 2 kilocalories per mole. Improvements in the neural network algorithm could also increase the accuracy of this method. In the future, an efficient and accurate approach to calculating two-body quantum mechanical interactions between residue pairs with NN potential energy surfaces should be developed, meaning the molecular mechanics would no longer be necessary. This would allow for the accuracy and efficiency of neural networks to be applied to all components of the protein energy calculations.